Hi guys, hope you all are doing well. Today we are going to derive an equation called as Mayer's equation, as you can see on the screen. And the equation is pretty simple. It's Cp minus Cv is equal to R. Just before we begin, in case if you haven't subscribed my channel, then kindly do it and place a comment if you find any positive or even a negative feedback. Okay, so let's get back to the derivation here. Before we derive, you are supposed to know three things. That is, one is the Cp, Cv, and the first law of thermodynamics. So this is the three things which you should be knowing. Okay, what these three things are. Now this Cp is called as the molar specific heat at a constant pressure. Cp is molar specific heat at constant pressure. Cv is molar specific heat, same thing, molar specific heat at constant volume. And R we already know, it's a universal gas constant which has a fixed value. And the first law of thermodynamics says that dq is equal to du plus dw. This is the first law of thermodynamics, where dq stands for heat energy, du stands for internal energy, and dw stands for work done. So this is first law of thermodynamics. Yes, definitely all these three aspects will be discussed by me in some other video, but as of now, in order to derive Mayer's equation, we are supposed to know these three things. So let's get to the derivation part here. So the proof begins with what Cp is. So Cp is molar specific heat at a constant pressure, and in your previous grades you might be accustomed to this formula. Cp is equal to dq, that is the amount of heat energy, upon n dt, where dt is temperature. So I'll just write over here, dq is the amount of heat energy, n is number of moles, and dt is change in temperature. So this is one of the formulas. Basically, specific heat is the amount of heat energy needed to raise the temperature of a body of a unit mole by 1 degree Celsius. Okay, so you can just go back and listen to the definition part of the specific heat. Now when we talk about gases, there are two kinds of specific heat. One is Cp and the other is Cv, and the amount of energy needed is different when the pressure is kept constant and when the volume is kept constant. So we have two formulas for this. One is molar specific heat at a constant pressure, and the other is molar specific heat at a constant volume. The formula remains same. The only difference is this is the heat energy supplied, and this is the change in the internal energy. So this is your internal energy. Now again, internal energy, first law of thermodynamics, all these are topics to be discussed separately in a separate video, but as of now we are trying to derive Mayer's equation, so just focus on those things. Now I'll just keeping dq on one side, and the n and dt are moved on the other side, so you get dq is equal to n Cp dt. And similar manner, Cv is equal to du upon n dt, so I can write du as n Cv dt. So n Cv dt, so n comes here, dt comes here, so I get n Cv dt. I'll call this equation as 1 and equation 2. Also, I am supposed to find out dw, which is equal to pdv. That is the amount of work done is nothing but pressure into change in volume. So this is your change in volume P stands for pressure, dW stands for work done. But we know this, that PV is equal to nRT is our ideal gas. This is our ideal gas equation. So if there is a change in volume, there must be change in temperature, because N and R are always a constant. So N is a constant, R is a constant. So if the volume is changing, that means the temperature must change. So this is what is called as the differential form of writing an equation. So if PdV is equal to nR dt, I can just replace PdV as nR dt. So I get dW is equal to nR dt. So this screen is something really important now. You have dq, equation number 1. You have du and cv dt, that is equation number 2. And dW as nR dt is equation number 3. And if you see, we have purposefully found out all these three things because we are going to substitute all these three equations into first law of thermodynamics. So if you see, I have applied first law of thermodynamics here, which says dq is equal to du plus dw. Now from 1, 2 and 3, what we are going to do is, we'll put all values of 1, 2 and 3 into this particular equation. So dq is ncp dt, du is ncv dt, and dw is nr dt. Now I can see that dt is in each term, so I can cancel dt, 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 n, and n. So what remains is cp is equal to cv plus r, which gives me cp minus cv is equal to r, which is the Mayer's equation. So this is a very small derivation. Yes, this equation we are going to utilize in finding out the specific heats of gases, then gamma of gases, that is the ratio of specific heats, and in order to explain few phenomena, we can utilize these equations called as Mayer's equation. So in order to derive this, just keep in mind that we are supposed to apply the first law of thermodynamics. dq is equal to du plus dw. I would write here. Just remember that we are supposed to apply dq is equal to du plus dw. Then try to find out dq, du and dw. So dq is ncp dt, du is ncv dt, and dw is nr dt. So just manipulate those things and you just move around with this equation and you will get that part. So I hope you have followed this part. Just make sure equation 1, 2 and 3 is confirmed to you. Anyway, this would be a very short video. Thank you so much for listening. If you are liking the videos, then please do subscribe and follow the channel in order to get further updates. Thanks. Bye.